Welcome. In this video I'll go through plasma waves and continue with where the previous video left off and try and linearize ideal MHD and show how this works in homogeneous plasmas, so where you have a uniform plasma with a constant density and constant pressure, and then show that there are three kinds of waves that you find in ideal MHD. These are Shear-Alfvén waves, which are kind of like waves on a guitar string going along magnetic fields. There are fast magnetosonic waves, which are compressional waves, so the plasma is being compressed perpendicular to the magnetic field. And then there are slow magnetosonic waves, which are where the plasma is compressed along the magnetic field, and that reduces to essentially the sound wave when it's along the field. So the way that we're going to start is by, like last lecture, we're going to assume we have a stationary, uniform, so homogeneous plasma. Because it's stationary, we just say that U naught, which is the equilibrium flow, is 0, and it's uniform, so homogeneous. And so we have the gradient of the equilibrium pressure is 0, and the gradient of the equilibrium mass density is also 0. Because it's homogeneous, we can also therefore use Fourier transforms. So we look at waves which have a particular wavelength. So we have a kind of wave like this, which has some kind of wavelength. There's a wavelength lambda, and we're going to write it in terms of the wave number. So k is 2 pi over lambda. And similarly in frequency, so we'll look at the angular frequency, which is 2 pi f, where f is the frequency in hertz. So this is the wave number, wavelength. And we're going to write all perturbed quantities. So, so for example, just to recap, the density is an equilibrium density plus a small perturbation. And the perturbation might depend on space and time. Whereas in this plasma, rho naught is just a constant, because it is not changing in time and it's not changing in space. And we're just going to write the perturbation as a Fourier series, so x and t. And this is the Fourier transform in space and in time of, I'll put hat here to mean the Fourier coefficients. So x becomes a k. In general, that's a vector. So we have a wave in any of the three directions, and it's a function of omega, which is the frequency. And then we have an e to the I k dot x minus an omega t. And then we're integrating over k and over omega. Okay, so we're going to take the Fourier, so Fourier transform. And then we can apply this to all the equations. So, for example, if we take the density equation, so in a uniform, well, let's write the density equation. So we have d by dt of delta rho, and then on the right hand side we have a minus u naught dot grad delta rho, and we have a minus rho naught, and then divergence of delta u. And we'll have a delta u dot grad rho naught, and finally we'll have a delta rho times divergence of u naught. So this is just the four terms, all of them linear, and now we can apply some of the assumptions we made. So we said u naught is equal to 0, so that goes, and that one goes, and then we've said that the gradient of rho naught is 0, so that also goes. And so we're just left with this equation with the d by dt and a rho naught divergence of delta u. And now we can Fourier transform this, so take integrals in dk and d omega, and we'll just write this as essentially we have a d by dt of this double integral. This will be a delta rho hat, k and omega. There should be brackets in here. dk d omega. And then on the right hand side we just have minus rho naught, and then here we have a divergence. So I've just substituted in the same expressions for delta rho into here, and a very similar expression for delta u into here. So we can have a Fourier transformed version of it. So we got delta rho hats and delta u hats, both all functions of k and omega. Okay, now we use the fact that this is these are Fourier coefficients here. So d by dt of this component doesn't depend on time, and so the only factor which does depend on time is this I omega, and so this brings down an I omega. So basically d by dt brings an additional factor of I omega in here. And same when you take a divergence, so taking a gradient in space, this will bring down an extra factor of k in here. So here you get a k divergence will essentially be replaced with a k dot inside this factor here, because again this part doesn't depend on x, only this part up here. So you get an I coming here, and then a k. And here you get an I times a minus omega, so this becomes a minus omega here. And so if you write out this equation, I'll take the integrals outside, so you end up with the integral of, I'll put here, so we have a minus I omega times a delta rho hat. And then move this over to the other side to make it easier to write this. So we have a rho naught, and then we have a ik dot delta u hat, because it's this component here, and all of this is still multiplied by e to the I, so k dot x minus omega t, and all of this is still equal to 0. Okay, so then the last step is just recognize that the only way of making this 0 is to make this part in the middle, so I use a different color, is to make this part here 0. And so we have an equation which is just that minus I omega delta rho hat is minus rho naught I k dot delta u. So you can see it's the same equation we would have got if we simply replaced d by dt with minus I omega and replaced divergence with I k dot, and that's what you get at the end. But the justification is that you can write it out as an integral like this, and then just say that this argument must go to 0. And then you can do the same thing for the other equations, so I'll just write them out. But it's the same process. So I've write out the other equations for the momentum, pressure, and magnetic field. So the next step is to choose one of these equations. Usually it's the velocity one is most convenient, but it could be any of them, and substitute all these components here. So we substitute this into here, so the delta p, and to replace this, and we substitute the magnetic field perturbation into here. And so we try and get an equation which only depends on delta u. So we're trying to eliminate all delta p's and delta b's, and note that delta rho doesn't actually enter into these equations. So the important ones are already this set here. So we just substitute these equations in. What we'll get is an equation with again an omega squared on this side. So because if each of these terms has an I omega, so we could multiply through by I omega, and then you have I omega delta p hat substitute into there. So this is the equation I've just substituted in these equations here, and then there's a bit of vector algebra to write this out here, but it's fairly straightforward. Sit down and wait out for a bit. So this equation here will now look at what kind of solutions this has, and you can see that this equation consists of everything in terms of delta u's and omegas and k's. So this is going to tell us something about what waves we have in the system. So we make some approximations first and just see what kind of limits there are. So first we'll assume is if k is along b, So K is along B. So we have a wave propagating along a magnetic field, and we have K is perpendicular to the motion. So we have a wave where we have a magnetic field going this way, so this is B naught, sorry, the equilibrium field. So the wave is propagating in this direction, and the plasma is moving in this direction, so delta U. And this is of course going to be a shear Alfvén wave where the plasma is oscillating and going along the magnetic field. And this simplifies quite a lot of things. So all this B naught dot delta U, that goes to 0. K dot delta U goes to 0. So we have K K dot B is not equal to 0, but delta U dot B is equal to 0. So let's see, so B naught dot K, this is not 0. This second term is 0 because you have delta U dot B here. And this term here is 0 because K dot delta U is 0. And same K dot delta U here is 0, K dot delta U. And so the only term that's left over is basically this term here, because all the other terms have gone to 0. So this is this term here. And B is parallel to K, so this is just B naught squared times K squared. And so we have an equation where we have on the left hand side we have minus omega squared delta U. And on the right hand side we have minus B naught squared. And here we have mu naught rho naught and a delta U with a K squared. Okay. So there's a simple wave where we have omega squared over K squared is B naught squared over mu naught rho naught, and this is the Alfvén speed, so V Alfvén squared. And this is called a shear Alfvén wave. And so you can recognize a few of the terms in this equation here. So this same speed appears here. So this is Alfvén speed squared. So it's V Alfvén squared. And very shortly you'll see that this term here is also a speed. This is the sound speed squared. So it's CS squared. So you have sound speeds, you have Alfvén speeds. In this case, you have a shear Alfvén wave from this term. So we can look at other limits. So if we have, what if we have K also along B? So we have K along B. So let's go with that. So K is along B, but now we have delta U along B. For example, so K and delta U are in the same directions. So B and delta U are all in the same direction. So all these are in the same direction, and so we can essentially get rid of all these vector quantities and just write them all as scalars because they're all in the same directions. And so the whole equation just reduces to. So I just replaced all the dot products with scalars because they're all in the same direction, and you can see that this will all cancel out. So so these two, for example, I get a different color here. So these two terms are the same; they cancel, and then this term is also just the same; it just cancels with this one. So here we have B naught squared over mu naught rho naught, cancels with this V Alfvén squared. You have K squared U naught. So this all cancels with these four terms all cancel out. And what we're left with is basically a sound wave. So we have a simple equation where we have omega squared over K squared is just sound speed squared. So it's a non-dispersive wave. All the wavelengths travel at the same speed, and it's all the sound speed. And so this is a wave where you have compression of the plasma along the field line. But it's the same as if it was in just a simple fluid. So you have a field line like this. So B naught is that direction. K is this way, so the wave is propagating this way, and it's just a compression wave. So you have like plasma fluid being compressed and expanded and compressed and expanded, for example. So if these are essentially the wave being this like motion of the plasma, and it's compressing the plasma and then expanding the plasma, compressing, expanding, and the wave is propagating along the field line like a standard sound wave. Okay, so the last case we want to look at is if we have a similar kind of wave, but we have instead k is perpendicular to b. So i.e. k dot b is 0. And the same that delta u is along k, and so delta u dot b is also equal to 0. You can see what this does to simplify these equations. So if you go back to this one here, so now delta u, this term is all 0. So these terms all go to 0 because you have b naught and k are perpendicular. B naught and u are perpendicular, so this second term is all 0. This term is now just all in the same direction, so it's just k times delta u, and this is k times delta u. And so we just have this first line here. And so this reduces to, I can show you over here. So we have, on the left hand side we have an omega squared. Both these terms give us k squared, and you have just a sound speed squared times and an alpha speed. And so you end up with an equation for a wave which is the sum of the alpha and sound waves. So you end up with omega squared over k squared is sound speed squared plus the alpha speed squared. And this is the fast wave. Essentially it's like a sound wave, except you're compressing the plasma fluid, which is where the sound wave part comes from, and you're also compressing the magnetic field. And so you end up with an alphane speed, because this is basically from the plasma magnetic field pressure. So it's the thermal pressure and the magnetic field pressure gives you this combined wave. And so you have the B naught this way, but now we're compressing the plasma in this direction. So we end up with compressed plasma and field lines, and expanded plasma and field lines this way. So you have a compression this way, and the wave is traveling perpendicular to the field line. So K is this way. So you have a fast traveling sound wave. Now in general, the wave can be at some angle to the field lines, so rather than either perpendicular or parallel. In general, you have an angle between them. So in general, you might have a field line like this with B naught, and you have some wave traveling like this. This is K at some angle theta to the wave. In this case, you end up with again the two solutions. So one corresponding to the sound wave along the field lines, one corresponding to the fast wave perpendicular to the field lines, but now they're kind of mixed together. So you've got two solutions, a slow wave and a fast wave, and these are both magnetosonic waves, magnetosonic. Because they're a sound wave, so sonic, and they involve magnetic fields, so magnetosonic. This one corresponds to the sound wave. So if theta goes to 0, you just end up with just a CS squared here, and this one goes to the fast wave. So you end up with V alpha n squared plus CS squared for the frequency. So yes, those are the two waves. So you have a fast wave and a slow magnetosonic wave, and you have a shear alpha wave.